Swayam Prabha. Digital India. Educated India.
Hello everyone, now we will discuss on the topic transmission of pollutants in environment part 2. In the part 1, we have seen that pollutants get entry into the environment in water, in air, in soil, and these are transmitted from one place to other place and particularly gets entry into the human body and any other living organisms and creates different types of impacts. And now, we will discuss on the transmission of groundwater contaminants, hydraulic gradient and groundwater flow, retardation and transmission of surface water contaminants. So, now we will see what is aquifer and how the groundwater is contaminated and how the contaminants transfer from one place to other place. So, an aquifer is a body of rock and or sediment that holds groundwater. So, you see the figure here. So, this is unconfined aquifer and this is confined aquifer, and in between we have one low hydraulic conductivity confining unit. So, and this is very low hydraulic conductivity bedrock. So, this is our bedrock and we are having here some layer, that is your confining layer, and we are showing here unconfined aquifer and confined aquifer. An aquifer is an underground layer of water bearing permeable rock fractures or unconsolidated materials. Groundwater from aquifers can be extracted using a water well. So, here we can anywhere we can put an well, so that water can be extracted from that place. So, this is a definition of aquifer and which provides water, and water can be extracted through the well. Now, the contaminants may enter into this groundwater. How? Through the percolation. Okay. So, groundwater contaminants occur when man-made products such as gasoline, oil, road salts and chemicals get into the groundwater and cause it to become unsafe and unfit for the human use, and materials from the land surface can move through the soil and end up in the groundwater. So, percolation takes place. Okay. So, hydraulic conductivity of the soil play a role to allow the water to go from the surface to the aquifer through the surface layer, and these are the different activities. So, oil spills, urban runoff, industry, municipal sewage, okay, sanitary landfills, and then illegal dumping, agricultural chemicals and septic systems, all are responsible for the creation of pollutants which can enter into the groundwater through this percolation process. So, water is penetrated through the soil bed and then reaches to here, and once it is reaching here. So, some pollutants is coming in this place. So, it may reach to this place first, and from this to this it will be moved. So, that transmission will be taking place, or it may also if this is our water table. So, it can be at the above of that water table surface soil we will be getting, there also the water can transmit from one to other place, the pollutants can transmit from one place to other place. So, here it is very clear, you see this is our datum plane, and say this is one well, another well is here, or we can say this is our water table, this one. So, from the datum plane we are getting different height. So, if we take consider 2 points, point 1 and point 2, in between this height is more here. So, water will be flowing through this. So, it may be below the water table or maybe above the water table. So, this is your groundwater surface, this is your water table. So, here also the transmission of the water will be there, water pollutants will be there, here also the transmission of the water pollutants will be there. So, the gradient, the difference in the head is giving the driving force for the transmissions of the pollutants in this water or in the subsoil layers also. But subsoil transmission is not so easy, it is a complex process and the structure of the soil will influence along with this gradient. Okay. So, most contaminants are introduced to the surface by percolation through soils, that just I have told you, and most contaminants are introduced to the subsurface by percolation through soils, and the movement of contaminants through the subsurface is complex and is difficult to predict. The most common mode of contaminant migrations in subsurface is advective flow, just like your transmissions in atmosphere, here also advection or advective flow a significant role for the transmissions of the pollutants in the subsurface also. And then the advective flow velocities are based on the average properties of the sublayer or aquifer materials and the average hydraulic gradient causing the flow, just del H and the structure of the sublayer. And when the pollutants are in the water, then also there may be some mechanical mixing or diffusion, etc. So, once below the water table, contaminants are also subjected to dispersion, that is mechanical mixings with uncontaminated water and diffusion or variations in the concentration. So, these are the basically the driving force which helps the transmissions of the contaminants in the groundwater. Now, how will mathematically represent this phenomena? Just like say in case of transmission of pollutants in atmosphere, we have developed some mathematical relationship, the people have developed and we have discussed on it. So, similarly, in this case we will also make some discussion how the pollutants are transmitted in the aquifer. So, contaminants like other dissolved solutes in groundwater also move on a smaller scale than calculated using Darcy's law and bulk values of aquifer properties. So, when we think about the subsoil, so here it is a porous bed. So, flow through porous bed, the Darcy's equation is applicable. So, for groundwater flow that equation can be applicable, but what happens, you see dispersive mixing causes some contaminant molecules to move ahead of this longitudinal to the average advective velocity along the hydraulic gradient and some molecules to move laterally to the hydraulic gradient. So, the net effect is the spread, the disperse the contaminant plume above the advective front. That means, that will be just like a plume structure which we have discussed in the transmission in case of atmosphere. So, here the similar type of plumes are also formed, and we can define hydraulic gradient as del H by L, that is equal to H 2 minus H 1. So, we have a datum line. So, here if I have say water table if it is, so H 2 and this is say H 1. So, H 2 from this place it is H 2, from this place it is H 1. So, this H 2 minus H 1 is the del height. Okay, so, this is del H and by L, this is the distance. So, this is the hydraulic gradient, where L is the head at location 1 and H 2 H 1 is the head at location 1, H 2 is the head at location 2 and L the distance between 1 and 2. So, this is the hydraulic gradient which is responsible for the transmission, and Darcy's law we know that V is equal to K into del H by L. So, this is the hydraulic gradient multiplied with some constant divided by L. So, that K is called hydraulic conductivity. So, the K is equal to called hydraulic conductivity and V is the groundwater Darcy velocity. Okay. So, what will be the flow rate? What will be the flow rate? So, that is equal to V into A. say if we have one say cross sectional area is A in the aquifer and V is the direction and V is the velocity of water, then V into A is the flow rate in this direction. So, if we have say like this, so 1 and 2, so this direction. So, what is the A in this and multiplied by V, that will be our Q from this to this. So, higher head to lower head. So, this will be the flow of the water along with the pollutants as well. So, these are the different values of the porosity and the hydraulic conductivity. As we mentioned that the porous structure of the aquifer materials will be responsible for the flow of the water as well as the pollutants, and similarly the hydraulic conductivity here we have discussed, that is also responsible, and this table shows the values, typical values for different types of materials present in the aquifer. Okay. So, now we see that when the water moves, then pollutants present in it may be equally move with the velocity or may not be able to move equally with the velocity of the water or water molecules, because there will be some interactions between the aquifer materials with the pollutants. So, if there is no interactions, that is theoretically the water velocity and the velocity of the pollutants will be same, and we see here if we have here the water is going on. So, these are the pollutants and these are the materials. So, these materials may have some interactions, and if there is no interactions, so all will go, there will be no variations, all water and pollutants will go, but if there is some interactions, the pollutants will be adsorbed by these materials present in the aquifer. So, the front head if we see, the pollutants may be the amount of materials passing through this will be reduced. Okay. So, that is called the retardation. So, that is called the retardation. The chemical retardation occurs when a solute reacts with the porous media and its rate of movement is retarded relative to the advective groundwater velocity, and retardation can occur by a variety of processes including adsorptions and precipitation. So, retardation rates of contaminants are likely variable and typically range from 0 to 10 times slower than the advective groundwater velocity. So, these are some typical velocity, that sometimes it may be 0 and sometimes it may be up to 10. And it has been said that some solvents like say TCE and PCE, which are trichloroethylene and perchloroethylene, they can sorb onto particles of the organic carbon present at the aquifer matrix. So, that is the reason why the flow of the pollutants will be lower, the velocity of the pollutants may be lower than the advective velocity of the water, and retardation can occur. Then how to quantify this retardation? We have used one factor, that is called retardation factor. So, what is that? The ratio of total contaminant in a unit volume of aquifer to the contaminant dissolved in groundwater. So, you have some aquifer. So, per unit volume we take, then what is the concentration and what is the concentration in the whole water. Okay. So, dissolved material concentration in the water C2 and C1 is the concentration of the pollutants in the unit volume of the aquifer. So, here water and materials will also be available. So, if it is 1, the ratio is 1, that means all the contaminants are dissolved in the water, but if it is 5, that means all pollutants or contaminants are not dissolved in the water, some are associated with the materials, aquifer materials. Okay. So, if it is 5, then 20% is dissolved in the groundwater and 80% of the pollutants are dissolved in this material. So, this is the concept of retardation factor, and more the value of retardation factor, lesser the solubility of the pollutants in the water. So, the availability of the water in the downstream will be lower, and in this the relation R is equal to V dash water by V dash contaminant, that is equal to velocity of water and then velocity of contaminant. So, that way also we can define. That means, certainly the if it is captured by the materials, this velocity will be reduced. So, that velocity of water by velocity of contaminants, this ratio also give us the R value. Okay. Now, we will discuss the transmission of surface water contaminants. So, in the previous class we have seen that when the pollutants get entry into the surface water through some drain, say the pollutants are getting into the river, then immediately here the pollutants BOD values increases and microbes start to work on it, and DO concentration reduces and it reaches its minimum DO values, and again the DO value increases because there are two processes, re-aeration and deoxygenation. So, re-aeration from air, oxygen enters into the water, and deoxygenation means the oxygen is consumed by the microorganism to degrade the organic compounds. So, in the water two opposite phenomena goes on, and gradually the requirement of oxygen or consumption of oxygen by the microorganisms reduced, and ultimately, but the re-aeration rate remains constant. So, gradually ultimately reaches to the saturated DO level. So, that we have already discussed. Now, we will be discussing how can we predict the DO level at any location downstream of this entry of the pollutants in the river stream, how these pollutants are distributed or how these pollutants are transmitted. Now, we see we had a river. So, another point from discharge point from municipal sources, it is coming here, say, and we have a river 1, this is our waste stream and this is our river stream. So, after that immediately it is mixing. So, our initial concentration we are getting this after mixing, here the microbial activity will start and gradually those will be the pollutants will be converted. So, here different types of phenomena are going on, organic compounds are being degraded by the microorganisms. Okay. So, concentration will vary, maybe precipitation etcetera. So, that way we will see how this phenomenon is going on. Now, say two stream we have, one is your waste stream, another is your river stream. So, this river stream is having a QR flow rate and then DOR dissolve oxygen in the river stream, and LR is the BOD in the river stream, and then QW is the waste flow and DOW is the DO in waste and LW is the BOD in waste. So, after this when it is mixing here, so ultimately we will be getting Q mix. What is Q mix here? Q mix is equal to QW plus QR, and DO mixed DO and LA mixed BOD, we can calculate this by mass balance. So, we can predict the DO at any downstream location or at any time. So, for that we need to determine the initial conditions, these are the initial conditions, and then determinations of the deoxygenation rate. As we know, there are two major phenomena, one is deoxygenation, another is re-aeration. So, we have to measure both rates. Okay. So, determination of re-aeration rate from the stream geometry. So, river stream geometry will help us to get the value of the re-aeration constant, and by doing some BOD test we can get the value of deoxygenation rate, and calculation of the DO deficit as a function of time, that we have to do as a function of time, what will be the deficit, DO deficit, and calculation of the time and deficit at the critical point, worst conditions. So, when the DO will be the minimum. So, that way we can calculate. Now, we have to use ultimate BOD, that is which is measure of the total organic content present initially for DO predictions. Now, you see the same figure shown here. So, this is waste, this is river and this is mixed. So, what will be the mass balance? The sum of the inputs is equal to sum of the outputs, is there is no reactions and no loss. So, this is the condition. So, what we are getting QR DOR with respect to dissolved oxygen balance. So, this is for this stream and this is QW DOW, it is equal to Q mix DO mix. Okay. So, Q mix is equal to QR QW. So, what will be the DO mix? DO mix equal to QR DOR plus QW DOW divided by Q mix, and Q mix is nothing but QW plus QR. So, put it here. So, we are getting the DO mix equal to this expression. Now, this DO mix we can represent it in terms of deficit. So, what is that? Deficit equal to what is the saturated dissolved oxygen value minus the DO actually available in the mixture. So, DOS minus DO mix, that is equal to DA after mixing what is the deficit oxygen, deficit of oxygen. So, DA is equal to, so we are getting DOS minus DO mix, DO mix. So, DO mix we replace this one. So, this expression we are getting here as DA. So, DOS we know that saturated value and it will depend upon the temperature and conditions. So, that we can get from any reference. So, like say Gilbert Masters we can book, we can refer to get the value of this DA. Normally it is say around 9 ppm. So, at normal condition, and similarly applying the mass balance on the organics over the relevant control volume, initial ultimate VOD concentration after mixings, that is LA, we can calculate LA into QW plus QR, that is equal to QW LW plus QR LR. So, that way we can get the value of LA and also you can get value of DA. Initial value determination is done. Now, we have to determine the value of re-aeration rate and deoxygenation rate. Okay. Now, re-aeration rate, always oxygen is coming from the atmosphere to the water. So, in that case the governing expression is dC by dt equal to KLa into Cs minus C, where KL is the gas transfer coefficient, oxygen is being transferred from the atmosphere to water, because concentration of oxygen is more in case of atmosphere. So, Kr is the re-aeration coefficient and Ct is the concentration at time t and Cs is the saturation concentration from Henry's law. So, what is the saturation concentration of oxygen in the water minus what is the concentration of any time t, that is our driving force, multiplied by Kr, that is equal to nothing but re-aeration coefficient, and this Cs minus Ct is nothing but the D deficit. So, this is the expression dC by dt equal to KRD. So, greater the deficit, greater the rate of transfer of oxygen from the gaseous to the aqueous phase. Now, what will be the value of Kr? Kr value depends upon the geometry of the streams. If we know the velocity, that is average stream velocity, if we know in meter per second, and if we know the average stream depth in meter, then this formula can be used, that is your Corner-Dobbins correlation. So, Kr is equal to 3.9 u to the power half by h to the power 3 by 2. So, by that way we can calculate the value of Kr, and temperature may vary. So, Kr correction is needed. So, Kr equal to Kr 20 into theta to the power T minus 20, when Kr 20 is the re-aeration constant at 20 degree centigrade and theta value is equal to 1.024. Then deoxygenation rate. So, deoxygenation rate will be proportional to the BOD available. Okay, more the BOD available or more organics available, more will be the degradation. So, rate of deoxygenation is Kd into L theta, where L theta is the ultimate BOD remaining at hydraulic retention time theta, and Kd is the deoxygenation rate coefficient per day. And here also this Kd value we can make some correction for temperature. So, Kd equal to Kd theta, Kd equal to Kd 20 theta to the power T minus 20. So, here Kd 20 is the value of deoxygenation rate constant at 20 degree centigrade, and theta value is 1.135 when the T is between 4 and 20 degree centigrade, and 1.056 when T is between 20 and 30 degree centigrade. So, these are people have already worked on it and they have given these recommendations, and this is mostly used for the calculation purpose. And then if we do the mass balance now, we have dd by d theta, how the deficit is changing. So, one method, that is your deoxygenation, another method is re-aeration. So, deoxygenation is reducing the concentration and re-aeration is increasing the concentration of oxygen in the water. So, the difference basically will be dd by d theta. When we have more value of deoxygenation, then we will be our deficit will be increasing, and then when this value is less, then deficit will be decreased and ultimately saturation value can be achieved. So, this is the expression, governing expressions which can be used to calculate the deficit. Now, rate of change in DO deficit is equal to the deoxygenation rate minus the re-aeration rate I have just discussed, and the deficit increases when there is more organic content due to degradation of organics in the presence of oxygen by microbes, and deficit decreases due to re-aeration, just we have discussed. And if we get the solution of this, the solution will be like this: d theta at time theta, the deficit is equal to k d L A by k r minus k d into e to the power minus k d theta minus e to the power minus k r theta plus d A into e to the power minus k r theta. So, all these terms we have already defined. So, knowing the values of this term, we can get the value of d theta. Now, we need to calculate the critical value, because we have seen in case of river. So, when the stream is coming and river is flowing, so in that case the DO reaches maximum and then again attains the saturated value. So, this point at the minimum point. So, what is the this minimum point, at what distance this will happen, and what will be the D value at this point. So, that is our point of concern now. So, if we want to get, we have one mathematical expressions with time and d in the water. Now, if you want to get this point, then d d d theta should be 0. So, d d d theta should be 0. So, by that we will be simplifying, we will be getting the derivation d by d theta, and then we will put it equal to 0, and the corresponding theta value is theta c, and theta c will be 1 by k r minus k d ln k r by k d into 1 minus d A k r minus k d by k d L A. So, this is the expressions we are getting for theta c, or the critical time which will be required to reach the DO value at the minimum position or minimum value. So, by substituting theta c in the Streeter-Phelps equation, which we have, this is a Streeter-Phelps equation. If we substitute this theta c, then the d which we will get, that will be the d c, that is the critical distance. So, what will be the distance x, where the d will be the deficit will be the maximum. So, that we can calculate. So, d c equal to k d into L A by k r minus k d into e minus k d theta c and minus e to the minus k r theta c plus d A into e to the minus k r theta c. So, that way you can calculate the value of theta c and d c. Now, one numerical problem we have: a city of 2 lakhs people discharges 1.32 meter cube per second of treated sewage having an ultimate BOD of 28 mg per liter and 1.8 mg per liter DO into a river with a flow of 9 meter cube per second and velocity of 0.36 meter per second. Upstream of the discharge point, the river has a BOD of 3.6 mg per liter and DO of 7.6 mg per liter. The saturation DO is 8.5 mg per liter, KD is 0.61 per day and KR 0.76 per day. Determine the critical DO and critical distance and the DO at 17 kilometer downstream. So, we have to solve this problem. Now, what we need to do? We have to calculate after mixing what will be the initial DO or initial deficit. So, that we have to calculate. So, DO after mixing, we have calculated, we have seen in the previous slide that DO mix will be QW DOW plus QR DOR by QW QR. Similarly, if we put these values here, so QW is given here 1, that is a flow rate, waste flow rate. So, how much we are getting 1.32. So, 1.32 will be putting here discharge, and DOW is equal to 1.8. So, 1.8 1.32, and here we are having 7.6, that is BOD of river, and your what is the flow rate 9 meter cube per second. So, this is your 9 into 7.6 divided by this 1.32 plus 9. So, this formula if we put, then DO equal to 6.85. So, this is DO after mixing. So, what is the deficit? So, deficit will be saturated minus this DO value, saturated value is 8.5 minus 6.85 equal to 1.6 mg per liter. So, we are getting the initial DO value. So, initial ultimate BOD how much here, that is LA equal to QW LW QR LR by QW QR. So, here we will be putting the value, then we are getting 28 into 1.32 plus 3.6 into 9 divided by these two, 1.32 plus 9 10.32. So, we are getting 6.75. So, this is our initial ultimate BOD after mixing. So, saturation DO is given. So, no need to look up. So, this value is given, we do not need to look up, and ultimate BOD given, no need to calculate from BOD 5, and KR value is given, we do not need to calculate it from the geometry of the stream, and KD value is also given. So, no need to calculate corrections from stream geometry, and we also do not need to do the temperature correction, I think. Okay. So, we also do not need to do any further correction. So, what we will get theta c, directly we will put the values in this expression which we have discussed. So, 1 by Kr 0.76, Kd 0.61, Ln 0.76 by 0.61 into 1 minus dA. So, dA, the deficit how much we have calculated 1.6, and into this one 0.76 minus 0.61 and 0.61 into 6.75. So, it is becoming 1.07 day. So, problem asks for critical distance or distance at which deficit is maximum. So, deficit is maximum. So, then we will be getting when DO is minimum. Okay. So, residence time or the time, that is equal to x divided by u, x is the distance divided by u is the velocity of the water. So, at critical condition x c will be theta c into u, and x c is equal to what? It is already given that we have seen the critical point comes at theta c 1.07 day. So, at 1.07 day how long the water will flow, that we have to calculate. So, here this is our velocity 1.07 day, this is our time, and this is our speed we have to put. So, 0.36 meter per second, this is our velocity. So, this is our time, critical time. So, this is meter per second. So, convert it into hour. So, that will be multiplied by 3600, and then it is we are having day. So, we are calculating multiplying by 24 hour per day. So, we are getting x equal to this much or 33.28 kilometer, because this velocity is given into meter per second. So, these conversions are there, that is why. Okay, then what will be the dc now? We have got the xc, we have got the theta c. So, that theta c value we will put it here. So, once theta c we have got, so this value we will put it here. So, 0.61, 6.75, 0.76, 0.61 and e to the power minus k d value given, theta c value we have calculated and k r value given, theta c calculated, dA is 1.6 into e to the power minus this one. So, ultimately we are getting this equal to 2.82 mg per liter. So, this is our critical deficit. So, what will be the critical DO concentration? That is equal to saturated DO minus critical deficit. So, that we are getting 8.5 minus 2.82, that is equal to 5.68 mg per liter. Then theta we know that is equal to x by u. So, that is equal to, if I want to get the second part, that is 17 kilometer. So, what is the time requirement for that? Theta is equal to x by u. So, that is 17 kilometer into 1000 meter per kilometer, that conversion, and 0.36 meter per second. So, again into the same unit per day. So, we have done this. So, this is converted to 0.54 day, and DO at 17 kilometer, what will be? We will be putting the same, the deficit first, the deficit expression. So, at 17 kilometer will be this expression we are putting. So, deficit we are getting 2.42, then we will get the value of DO 17, that is dissolved oxygen equal to saturated DO minus deficit. So, 8.5 minus 2.42. So, that is equal to 6.08 mg per liter. Up to this in this class, thank you very much for your patience.